Next example is a hair dryer. A hair dryer is basically a duct that has an electric resistor in it. So let's sketch. We have a duct. It's a steady flow device. Air is getting in and flowing through resistors. And the power put into those resistors, electric power, we are given that 1200 watts. Now there is inlet condition. There are inlet conditions given to us, which is the air flowing in is at 100 kilopascal and 22 degrees Celsius. Exit at the air is 47 degrees Celsius, and exit area is 60 centimeters squared. Okay, we are told that there are no heat interactions taking place, and we are asked to calculate the volumetric flow rate of the air at the inlet and velocity of the air at the exit. Okay, let's take a look at it again. So our system is air. Air is flowing through a duct, and it is flowing through the electric resistors where it is heated, and its temperature was 22 at the inlet. It becomes 47 degrees Celsius at the exit. We are given the power of that electric resistors, 1200 watts, and inlet conditions given, and exit temperature is given, and exit area is given. So we are asked to calculate the volumetric flow rate at the inlet and then velocity at the exit. So how can we figure out volumetric flow rate at the inlet? Okay. So there is one equation. If we want to calculate the volumetric flow rate, we can multiply mass flow rate with specific volume. Okay. This comes from basically mass flow rate equation, where it is density times volumetric flow rate, but density is 1 over specific volume. We multiply it with volumetric flow rate. So basically mass flow rate is actually volumetric flow rate over specific volume. Okay, this equation comes from there. So if we want to calculate the volumetric flow rate at the inlet, we need to know the mass flow rate and the specific volume at the inlet. Well, since air is an ideal gas, what we can do is easily calculate specific volume using the ideal gas equation. Let's do that. R is, we look at from table A2, you can look at here. Oh my god, what's this? Okay, 0.287 kilojoule per kilogram Kelvin. And T is, this has to be in kelvins when you are dealing with ideal gas, right? And the pressure has to be in kilopascal, because the kilojoule here is actually kilopascal times meter cube. So therefore the pressure has to be in kilopascal. being very careful about those. Now we plugged in everything given and we can calculate the specific volume. It should be 0.8467 meter cube per kilogram. All right. Now the question is, there is mass flow rate and we don't know the mass flow rate. The only way to find the mass flow rate here is if we actually write down the energy balance, because in the energy balance, mass flow rate term is there. And we cannot use any other equation because we are not given area, we are not given velocity at the inlet. We cannot use any other equations, such as there are some equations to find mass flow rate. Those are 1 over specific volume times area times velocity at the inlet. But unfortunately, we are not given area and velocity, and therefore we cannot use this equation. The only way is actually use the energy balance to calculate the mass flow rate. This is kind of also getting hint from the question statement, because they are giving you the power. If they are giving you the power, they want you to pretty much write down energy balance. Okay, so let's write down energy balance for that steady flow device. But before doing that, let's analyze the energy interactions. The energies that are getting in are electric power and the mass. And what is getting out is the energy with the mass. I don't see any other interactions here in this problem. Okay, so we start with writing the general form of that energy balance. But when we are dealing with steady flow devices, generally the form of energies they are giving us are the rate forms. The reason is if they are giving you the rate forms of these energies like power or heat transfer rate, you should write down the rate form of that energy balance. And the reason for that is, as you guys can see, that since this is a steady flow device, the change with time in terms of the system properties like energy, internal energy, any other property like maybe enthalpy, like entropy, these are with time is not changing. So therefore you set this to 0 for a steady flow device, and in this case we are dealing with a steady flow device, which makes our energy balance as such that the rate of energy flowing in is equal to the rate of energy flowing out. And there is only two types of energies getting in this case the electric plus the mass. And mass energy of that mass is related to its enthalpy, and energy getting out is the mass. Remember something here. When I say subscript 1 and 2, that means 1 is inlet, the 2 is exit, first of all. Second is there is a 1 inlet, 1 exit here, okay? Therefore, there is one constant mass flow rate going on throughout the system, because the inlet mass flow rate has to be equal to the exit mass flow rate in a steady flow device. And if there is a single stream, because to keep the mass of that system same with respect to time, what is getting in has to get out, so that the mass of your system is not actually changing. So therefore, what is getting out has to be equal to what is getting in, and that means there is a one single mass flow rate. Therefore, those terms are actually the same. All right, so let's rearrange this equation, okay? So mass flow rate times enthalpy differences, and the change in the enthalpy, if we are dealing with an ideal gas, I can represent it as Cp delta T. Alright, so we can do that. Since the temperatures are given to us, delta T is given, Cp we can look at from table A2, I believe, and then we have given the electric power, so we can calculate the mass flow rate. Let's do that. So the electric power is in watts. We should convert this to kilowatts. Okay, so to calculate the mass flow rate, we are gonna divide the electric power to Cp delta T. Electric power is 1.2 kilojoule per second, which is watts, over Cp we look at from the tables for air. So the temperature is 22 at the inlet, 47 at the exit. Okay. What we're gonna do is we're gonna do some assumption here. Okay, we're gonna read a constant value for the specific heat. That because that is how we solve those integrals that we use to calculate the enthalpy change. So I need to assume a constant value for the specific heat, which is Cp, and I'm going to assume it at the value at 300 Kelvin. Okay, you can also do that. It is okay to do, because since inlet and exit conditions are given, 22 plus 47 over 2, which is gonna give you the average temperature. And from the average temperature, you can actually go to table let's see what the average temperature is. Okay, so we are given I'm calculating at the same time. So we are given 47 plus 22. Okay, so when we average the temperature, 47 plus 22 over 2, and convert it to Kelvin, we notice that temperature is approximately 300, okay? So that's the reason we actually read the specific heat value for ourselves in this question, okay? So we're gonna plug in 1.005. So this unit doesn't matter. It can be changed to Kelvin interchangeably because it's a degree change. For degree change, whether it's Kelvin or degree Celsius, doesn't matter. It's just a degree change. So, and the temperature change is 47 minus 22. And this should give us the mass flow rate 0.04776. Okay, so since now we know the mass flow rate, we know the specific volume, we can calculate the first part of this question, which is asking us to calculate the volumetric flow rate, which was mass flow rate times specific volume. And the units make sense because the final unit is meter cube per second, which is the unit of a volumetric flow rate. And the answer is 0.0404 meter cube per second. Okay, that is the first part. Now the next part is asking us to calculate velocity, and the only way to calculate velocity is through the use of the equation which relates mass flow rate to velocity. It is 1 over v2. I need to use exit conditions because I'm trying to find velocity at the exit. Okay, so the mass flow rate is equal to 1 over specific volume at the exit times area at the exit times velocity at the exit. Okay, so v2 by v2 I meant the exit velocity. Okay, so that is the only equation that has velocity in it, and since we know area, we know mass flow rate, if we can actually figure out specific volume at the exit, then we can figure out the exit velocity using this equation. Then the question is, how can we figure out specific volume at the exit? This is an ideal gas. If we know the temperature and pressure at the exit, then we should be able to figure out basically the specific volume. At this point, when I look at the question statement, so to figure out specific volume, remember we need to have the pressure known at the exit. Looking at the problem statement, it is not clearly stated in the problem statement, but they're also giving us the pressure at the exit to be the same as the pressure at the inlet. Okay, so this is not clearly written down in the question because I think that is what is really critical and that is missing in that question statement. But going back, we can add that the final exit pressure is also 100 kilopascal. Okay, when we do that, we can actually figure out the specific volume at the exit. The R is known. Temperature is known. And the pressure is we correct that as I said. Okay, pressure at the exit is the same as pressure at the inlet, and with that information we can figure out what the specific volume is. It's 0.9184 meter cube per kilogram. And now we know that we can figure out what is the velocity. Okay, but we gotta be very careful with the units. Okay, let's write down what is given to us. It is, we are trying to calculate the velocity. We can rearrange this to be mass flow rate times specific volume over area, and let's plug it in. 0.04776 kilogram per second is the mass flow rate. Specific volume is what we just found, and area was in centimeter squared, so we gotta be careful to convert that to meters squared, and this gives us exit velocity to be 7.31 meter per second. All right.